Hi everyone, I'm Mia. I'm doing Recitation 6, Part 1. Let's get started. RNNs can process sequence data for predictions. They have a lot of practical applications. For instance, you can use it to translate text from one language to another, even when it's not a word-to-word direct translation. RNNs can also translate speech to text and use a recent history of words that were spoken to predict what's going to be spoken next. They can also be applied to robotics to analyze information via sensors for environments, for navigation, real and virtual environments, and anything that uses time as sequential, so RNNs can be applied to audio and video too. We'll be using a sequence of words as an example for this part of the recitation. It is To Be or Not to Be from the play Hamlet by Shakespeare. The entire phrase is actually to be or not to be, that is the question. To relate CNNs and RNNs a bit, they're both feature extractors. We can make an interesting observation between CNNs and RNNs in that CNNs can consider the entire sequence article and is often used for things like speech to text, while RNNs take input sequentially and are commonly used for language-to-language translation. Okay, so we have the dictionary here, and the example phrase, to be or not to be. Here's the tokenized version. Really, the model thinks of these in terms of the dictionary. So 2 is 7, be is 1, or is 4, not is 3, and so on. And it goes a step further to think of them as one hot. We'll start at t equals 0. In this picture, there's only one node, but there are as many nodes as frequencies, like in homework 1. There's the hidden layer, and then we have the prediction. So here we might predict the word to in one hot form. The one hot is a label, so if the prediction was perfect, it would say that, but in actuality, it looks something like this. We can take the argmax of this, and we would get the correct values, and these logits are passed to the next time step. And what happens is that it feeds into the next time step over and over, and that's generally how RNNs work. For this very simple RNN, we're using the hyperbolic tangent function, which allows us to have outputs in the range from -1 to +1. This is useful for a loop, where values are processed over and over. However, these simple RNNs are prone to error because they only look back one time step. And in other words, they have short-term memory. So what do we mean by short-term memory? Here we can see that the word to would be fed into the RNN first. The RNN encodes it and then gives an output into a hidden layer. And then we feed B with the hidden layer from the previous step. The hidden state has information from all previous steps. So the RNN would now have information about the word to and B. And this process is repeated. The RNN keeps information from all previous steps. And the distribution of colors in this example illustrates the problem of short-term memory in RNNs. As the RNN processes more steps, it has trouble retaining information from previous steps. This is caused by the vanishing gradient. For example, it could have errors like to be : which is only part of the phrase and not in the right place. Or it could have an error like to be or not to be or not to be or not, etc. Because of this short-term memory, it's not able to use information from far back. The problem is after finding the error value and using it to complete back propagation to calculate the gradient. Each node in the layer calculates its gradient with respect to the effects of the gradients in the layer before it. If the adjustments in the current layer are small, then the adjustments in the next layer will be smaller, and gradients exponentially shrink as it back propagates through the network. Earlier layers can fail to do any learning if the internal weights are barely being adjusted. To reduce the amount of short-term memory in the RNN, we introduce variations like long short-term memory and gated recurrent units. Generally speaking, LSTMs are slower than GRUs. Oh, that says GNU. That should say GRU. Because they have more tensors. So we'll do a basic overview of LSTMs using our to be or not to be example. I've just expanded the same drawing, so it has more room. Okay, so we are adding here in the middle some memory because we want to remember what happens many time steps ago. The cross and X symbols are gates, where the cross represents element by element multiplication of vectors, and the addition of vectors, and the X represents element by element multiplication. Here we're using the sigmoid activation function, and in introducing this, we have previous predictions which are passed through for new predictions. Also, we have a copy that's being held for the next time step through the network, and some will be forgotten, but ones remembered will be added back into the prediction later. To combine our predictions with memories, we may need to be selective. We create a filter for that and another gate for selection so that we only pass a few for prediction during that time step. Lastly, we need to ignore some predictions and possibilities that come in. If they're irrelevant, they're set aside. Let's walk through an example. So this example is extremely basic. We'll assume that the LSTM has been trained and that we are now in the process of coming up with the opening line of Hamlet. Our new information is the start of the phrase to be or not to be, so to is the most recent word that has occurred so far. From this, we can deduce that the prediction to was made in the previous time step. And the first step towards the prediction is that we know the next word is either not to, so it's shown here as a negative 2, and that it could be the word be. Please remember it's a very simple example, so we could imagine that we ignore something irrelevant like that, or apple, or so we can set these aside, and the predictions are passed again. There's no memory at the moment, but the machine remembers information for the next time around. The selection then knows that B has a greater chance than it not being 2, and so the prediction B comes out. Now we'll go through with to be from the start of the phrase, to be or not to be. We can start to predict that what follows B is either or, the colon, or negative B, or not B. Again, we can ignore irrelevant information and pass the information along. This time, from the previous step, we know that our forgetting gate remembered that a previous option could have been the word be, shown as positive B here. But with our new prediction of negative B, the two B's cancel out. And so now we just have or the colon. From previous training, we might find that or has a greater probability than the colon. And so our prediction becomes the word or. And we have added to the phrase, so it now reads to be or. We did not go over the GRU, but to cover it briefly, it's similar to LSTMs, but uses a hidden state instead of the gates of the cell state. It has an update gate that's like the forget in LSTMs, and there's a reset gate that decides how much of the past information it forgets. This is an article that might be helpful for your homework. And that's all. And on to Sam. Thanks.